Welcome to the 7th chapter on control loops and invariants of the Logical Foundations of Cyber-Physical Systems textbook, in which we will advance the analytical understanding of cyber-physical systems to cover actual control loops. And the point is that our syntax and semantics already included loops, and we made good use of them in modeling purposes, but our analytic understanding hasn't caught up with it yet. All that we were able to do with loops so far in our reasoning was just to unfold them one step at a time. And that's only enough to understand loops that merely repeat some fixed finite number of control actions and a fixed finite number of repetitions, but all the exciting things that CPSs do are mostly in unbounded time horizons, reaching an unbounded number of control decisions. In order to ever have a chance to understand them, what we will be introducing in this chapter is the absolutely fundamentally important concept of invariants. And it turns out that our understanding of the language exceeds our understanding of the reasoning principles. We do understand many of these dynamical systems axioms really well, and we even understand proof principles about logical connectives such as AND. But for loops, not so much. The only thing we've seen is fixed unrolling of loops with the iteration axiom. And if our understanding of a language exceeds our reasoning principles, then in computational thinking, we would argue that we don't even actually truly understand an element of a programming language or a system model if we do not also understand ways of reasoning about them. In other words, our analysis capabilities really have to play catch up with our modeling skills. But that's precisely how this textbook is set up. We gradually understand CPSs one layer at a time and master that layer completely before advancing to the next challenge. Our next challenge are the control loops now. And this chapter will complete everything we ever need to know in terms of reasoning techniques for elementary cyber-physical systems. Why are control loops so important? Well, because they can inspect the current state of the system, take an action to control the system, then let physics evolve for a certain period of time, and repeat these steps over and over in a loop, which is precisely how you make feedback happen. And since control loops are responsible for a lot of the power of CPSs, the flip side is they can also be quite important and tricky to analyze. Because it's much easier to understand what a system does in one step than it is to understand what a system does when it's running for an arbitrary amount of time. This is essentially the CPS counterpart of the phenomenon that very short time predictions are much easier to get right than long-term predictions usually. For example, it's a lot easier to predict the weather in a second from now than it is to predict the weather of next week. With that, I'm really only repeating something that Niels Bohr already found out, that prediction is very difficult, especially if it's about the future. Now, the main insight to have a chance to analyze control loops that are repeated over and over and over and over again to get a car controlled to a destination far along, for example, is that, well, invariants are super helpful. By that, I mean properties that precisely do not change as time progresses. Because if we have an invariant, a property relationship or logical formula that is not changing at all as the cyber-physical system keeps on evolving over time, then even if the position, the velocity, the direction, everything in the system keeps on changing, then there's at least the one invariant quantity that we will be able to rely on. And that's why invariants also play a fundamental role in the design of cyber-physical systems. And it's also no coincidence that invariants, things that don't change, play a central theme also in many parts of mathematics, although in that case the invariants are of other mathematical structures. In our cases, they're invariants of cyberphysical systems. The point is, invariants will make it possible to reason locally about what we know in complete disregard of everything that ever happened in the past evolution of the system, because those are all captured and summarized by the invariants that are still true. Another important part of this chapter is that we will also be very explicit with sequent calculus proofs how the individual parts of the proof fit together, and also what impact different changes to preconditions and invariants of a cyberphysical system have on the proof, which is a useful opportunity for you to practice reasoning about these systems, but will also sharpen your skills to understand what part of the proof are essentially complete follow your nose. In particular, in the future we will be not doing them quite as explicit anymore, and what parts of the proof deserve a lot of conceptual attention, such as, for example, the question, well, what then is an invariant? But we're really getting ahead of ourselves here. What we're learning in this chapter is, on the modeling and control side, the fundamental concept of control loops. Without, go figure, there's no control, at least not for a very long amount of time. Also, we will understand feedback mechanisms that are fundamentally always implemented with some kind of control loop, and we'll also get an intuition for the dynamics of iteration. This chapter is big on computational thinking principles, no surprise here, because we will augment our rigorous reasoning techniques that we already have for CPSs to now also cover CPSs that involve control loops, thereby completely covering elementary CPSs. We'll learn how to identify and express invariants as very fundamental concepts in CPSs, because over the entire runtime of a CPS, many things can change in both the system itself and also the environment. So even if you just have a very few lines of code, if you just keep on running them over and over and over and over and over again, the entire state of the system and the world around it after, say, 100,000 iterations can look very different than it used to when you started. So even if there wasn't a whole lot of code running, the world changed quite a bit. If we now understand invariants, things that haven't changed even if we have run the loop 100,000 times, then that's the single most important insight and information about a CPS, because it tells us what we can still rely on even if the system loop ran 100,000 times, or 1,000,000 times for that matter, which will also be the beginning of design principles that essentially design the CPS around those invariants. We'll also see how important the distinction is between global versus local reasoning techniques. That basically determines how much we get to keep about the assumptions of the system. We'll also have ways of looking into finitely accessible infinities, because of course, the set of possible repetition that a loop could do is actually infinite, because it's one for any natural number, of which there happen to be infinitely many. We operationalize also invariant construction principles by working very systematically from an axiomatic development in dynamical systems axioms that we already saw. We'll also look at splitting generalization techniques. And on the CPS skills side, we're playing catch up with our understanding of the semantics of control loops, and will thereby develop a higher intuition for their operational effects of control loops. Now, the only thing we've seen as a reasoning technique for control loops was this one, the iteration axiom that says always after repeating a system alpha any number of times, as the non-deterministic partition operator says, are we safe? If and only if we're safe right now, and always after running alpha, it is the case that always after repeating alpha any number of times we're safe. That means in any state omega that we're in, a new state nu that the repetition of alpha can reach, that state will be safe for all of those possibilities. Whenever we start somewhere safe, well, that's a given for the left conjunct, but also when always after running alpha in any of the many possible ways that we could do that, it is the case that should we be repeating alpha again any number of times, we end up in a safe state regardless. Remember here, for example, the repeating alpha again any number of times could have been zeros. In particular, we're also safe right here. Well, that's a beautiful axiom. The only trouble with it is that if we use it from left to right, it doesn't exactly really simplify the question, because it says, oh, all we need to do in order to prove a property of a loop is to prove that we're happy right now, and then worry about what alpha could do in one control cycle, and then, oh, all you need to do is ask the exact same question again. If you think in terms of pictures, you'll understand why that's not completely helpful. If you would like to understand whether any number of repetitions are safe right here, we'll have to worry about being safe right now, and then we'll wrestle with the dynamics that one control cycle could have, and then over here, we're asking literally the exact same question again, which isn't a whole lot of progress. Well, I told you, if you take a deep enough analysis, you can actually surprisingly understand that from the right angle, this will already have been enough progress in order to do proofs. But that's really so subtle that I don't at this moment in time want to go into this. Instead, we'll develop a much more useful reasoning principle for loops. We still very much would like to prove and equivalently rephrase the question whether we are always safe after repeating alpha any number of times. So no matter where we go, we want to be safe. And of course, it was actually very clever to begin by saying, I guess we have to be safe right now, which means in the current state, the post-condition has to be true. That makes sense because, of course, if we're allowed to repeat alpha any number of times, this number of times could be zero, and so we only have a chance for this formula to be true if we at least start in a safe state. But then, what are we missing? What we're missing is that we're safe over here. In fact, that somehow this state is one that is safe no matter where we've come from here. But there's something we can assume at least. Although we will have to show here that all runs of alpha take us to safe states. In order to conclude that we're safe over here, we can at least assume something because, well, a moment ago we already invested effort to try and prove that we're safe at the moment at least, which means we only have to show that we're safe after all runs of one round of alpha under the assumption that we're safe at the moment, leading to this logic formula. Now we're saying we're safe after any number of repetitions of alpha, if and only if we're safe right now, and whenever we're safe, in one more round of alpha, are we safe again? That sounds like a good equivalence. Is it really, though? So let's write this down. This axiom says that we're safe after any number of repetitions of alpha. If we're safe right now, that makes a lot of sense. And under the assumption that we're safe at the moment, we're safe again after we run alpha for one round. And that is useful because it tells us, first of all, we're safe right now by the first conjunct, but then also if we're safe right now, which we are by the first conjunct, then all ways of running just one round of alpha is safe again, which enables us to conclude over here that that must also be a safe state. That's good. Does it suffice? Well, if over here we knew that if we're safe, then all runs of one round of alpha are safe again, then we would know that we're safe over there, but do we really know at this particular state, of which again there could be many, 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 that the implication if we're safe, then we're safe after one more round of alpha is truly true? No. because by implication, we're only demanding that in a state where this is true, that any number of repetitions of alpha are safe, we only ask ourselves whether we're safe right now, and whether in that one state it is true that if we're safe right now, then after all runs of one round of alpha are we safe. That's not quite enough. So we need to make sure that we have this implication available, not just here at the initial state, but also at that state, to make sure we know it here, and at that state, to make sure we know it here, and so on. And that's where we can make use of other differential logic constructs to say, after all runs of repeating alpha any number of times, if we're still safe, then we're safe after one more round. So that means over here, we know that we're safe, but because after any number of rounds of alpha repetitions, we know that if we're safe right now, then we're safe after one more round. Well, we are safe right now, it just said that, so we're safe after one more round. But because this formula here is true after any number of repetitions of alpha, we also know over here in this state that if we're still safe, then we're safe after one more round. Well, we are safe, so I guess we're safe after one more round. But over here, we also know that if we're still safe, we're safe after one more round, because the formula here says after any number of repetitions of alpha is it the case that we know that if we're still safe after one more round. So over here we also know that, well, if p, then after all runs of alpha p, but we do know p, so also over here we do know p, and so on and so on and so on and so on. No matter how many repetitions this thing actually made, we will, by induction, be able to conclude that because we started somewhere safe, and the safety notion was an inductive one, no matter where we went, if we were still safe, we're still safe one more round in the future. That means no matter where we're going, we must have been somewhere safe. This is the induction axiom that says we're always safe after repeating alpha any number of times if we start safe, and if, no matter how far we have already repeated alpha, if we are still safe, then we're safe after one more round of alpha, no matter how alpha is running. Beautiful axiom. And what's the catch with it? The catch is the axiom still says, so all you need to do in order to prove a property of a loop is to do some stuff and prove some other property of a loop. In other words, the inductive proof that after any number of rounds repeating alpha, we're safe, asks us to instead do a proof of this slightly more complicated postcondition for the exact same loop. It's still the case that all we need to do in order to answer a property of a loop is to answer a property of a loop. That was the problem with the iteration axiom already. But mind you, here we're just one step better, because we're no longer asking literally the same question about the loop that we used to ask over here. Here we have a postcondition P without any assumption, and here we have an, okay, admittedly slightly more complicated question to ask, but at least we get to assume something. We get to assume that we were still safe. So from an information perspective, the question has become a bit easier than it is over there. But we still need to be able to exploit that in proofs land. The intuition is that we'll now work hard to get rid of this repetition here. How we do that is by generalizing the induction step using Gödel's proof rule of generalization. If we have a proof of a formula P, then Gödel's proof rule tells us that we also have a proof of the formula that after all alpha runs P. Yeah, sure, that makes some sense. If we have a proof of P, then by soundness, P must be a valid differential logic formula, but that means it's actually true in all the states. If it's true in all the states, then it is also true in all the states that we reach after running alpha from any state, because, well, these are still states. In other words, if P is true in every state, then of course alpha P box is also true in every state. And that we can exploit in order to derive from the induction axiom we just saw, this induction core proof rule. that says if we assume to be safe in the beginning, then we're safe no matter how often we repeat alpha. In order to prove that, it suffices to find a proof that if we're safe right now, then after one more round of alpha are we safe. Notice this actually reduces the question about a loop to a question that is completely loop-free. At least it has one loop less than alpha star had. So in case alpha itself has more stars, well, I guess we need to repeat the same kind of argument further up the proof tree. But let's convince ourselves why this proof rule is an acceptable one. And it is a derived proof rule. So rather than going back to the semantics of differential numbering logic and doing a semantical proof, we can simply derive it out of the proof rules and axioms we already saw. How do we do that? Well, apparently we're starting with this question as the desired conclusion, and then we point to the repetition and expand it by the induction axiom we just saw, which rephrases equivalently to the question whether we're safe right now, and whether after any number of repetitions of alpha, if we're still safe, then we're safe after one more round. These were equivalent, right? So now what we do is prove the conjunction by the and right proof rule, which says the first question is whether we're safe in the beginning. Yeah, sure we are, because by identity, if we assume P, of course we get to prove P. That's easy. The right question remaining is this one. And now we use Gödel's proof rule to say that a property is true after a box modality for alpha star in this case. Here it was alpha. If we can already prove the post condition is true in every state. Notice here, it is very important that we remove the assumption we had by weakening ultimately, because of course, if we have Gödel's proof rule, no matter how many assumptions we have about the initial state out here, they all need to be deleted in the remaining premise, because we don't get to assume that after running the alpha box program, the initial state assumptions are still true. And likewise over here, I mean, the P is just telling us that we assume P was true in the very beginning before the loop ran. So if we're understanding the inductive step in it, we don't get to assume we're still in the initial state. That's the whole point. And that means over here, we need to prove that P implies that after all runs of alpha box P, precisely the post condition. But, don't you worry, because by using the implies right proof rule, we will get the assumption P back in the game again. So the remaining sub-goal, the only one of this proof, is exactly the one that we conjectured would be the only remaining premise up here, that if we're safe, then we're safe after one more round of alpha. Because whenever we invoke this proof rule, we could instead have copy-paste repeated this proof. We can from now on believe that this is a derived proof rule that we just use like so. What could go wrong is that even if this is a sound proof rule, if we have a proof of that, we also have a proof of this, it is no longer an equivalence. The induction axiom was an equivalence, and nothing could possibly have gone wrong with it, but we ruined that at the generalization step. When we're calling upon Gödel's generalization proof rule, we're throwing away a lot of information about the fact that in order to get to the state where we are worrying about the post condition, whether P implies that all runs of alpha satisfy P again, we deleted our knowledge that the thing we ran while doing that was exactly the alpha star program. That means sometimes we won't be able to prove with this proof principle, because we sometimes have to augment and carry more information around, which is where we get to the most canonical loop invariant proof rule. It goes like this. If we have a number of assumptions on the initial state, and possibly some alternatives that we could be proving instead, if we're trying to prove that always after repeating alpha a number of times we're safe, it suffices to, for some loop invariant J, prove that this loop invariant J is true in the initial state, well, or the alternatives work out, and to prove that if the loop invariant is true, it's true again after one round of alpha. And if when we're done with the loop at the end, we apparently still know the loop invariant, but we also need to prove that this loop invariant was strong enough to imply the post condition we were originally interested in. So in pictures land. We repeat alpha any number of times to some state. Over here, we would like to know P. What we do know is that we have a proof that the loop invariant J is true in the very beginning. That was this first premise. We also know that whenever J is true, after running one more round of alpha, J is true again, because this is a premise we prove without reference to the initial information that we have here. In other words, it's a global fact because it has a proof that implies by soundness that it's valid sequent. And that means no matter where we go, if J is still true, then in the next state, J is still true. J was true in the beginning, so I guess it is true here, but this implication is proved once and for all. That means next state we're still in a safe state satisfying invariant J. But since we are, because we still know that J implies all runs of alpha satisfy J, that we're satisfying J here again. At the end we thus know J, but by the third premise we also know that if we know J, then we're safe, which means over here we have essentially this implication that this corresponds, so that J implies P, and that means over here we also do know that the post condition P that we were interested in is true. That's the loop invariant principle. Let's also derive that it merely follows syntactically from the principles we already saw. Here is the loop. What we'll be doing is do a clever logical cut operation to prove that J implies after any number of repetitions of alpha, J holds true, and then we get to assume it, right? That's how the cut principle worked. And now, over here on the left-hand side branch, we do use the implies right proof rule to get this assumption to where it needs to go. We weaken some things away silently even, because we have already understood that we can always omit the assumptions that we would have had available and omit other alternatives that we're not deciding to prove. And so over here we have the remaining sub-question whether the loop invariant implies that after any number of repetitions of alpha, the loop invariant holds true again, and that's by the previous loop induction core proof rule precisely can be reduced to the question whether if we're in the loop invariant J, then after one more round, are we in J again? That we already saw was a derived proof rule, and that means over on the other side we have this fact available now because we just proved it. And then by the implies left proof rule, all we need to do is prove the left-hand side of the implication. Here we're doing that in order to gain the right-hand side of the implication. Here on this side, we weaken some things away that we're settling on not proving, which is always sound. And we only have the remaining question whether from the initial assumptions we can prove the loop invariant J, well, or prove one of the other alternatives that we would settle for again. Over on this side, we again also weaken initial assumptions and alternatives and all kinds of things away, and we're left with just the question that on the additional right-hand side of the implication that we have as an assumption, does that imply the original question, namely that after all repetitions of alpha, P holds true, as opposed to over here, after all repetitions of alpha, the loop invariant J holds true. Well, these two guys are very close. In order to close the proof, we now use the monotonicity proof principle that says that if we're trying to ask to prove whether after all alpha runs P holds true, and that implies that after all alpha runs Q holds true as well, it is sufficient to prove that P implies Q, because sure, if this post condition right here implies that post condition over there, then if we're assuming that after all alpha runs P holds true, then of course after all alpha runs Q holds true again. We use this monotonicity proof rule for this circumstance where alpha is alpha star to show that it is by monotonicity sufficient to prove that after all repetitions of alpha J holds true implies that after all repetitions of alpha P holds true, to simply prove that the J loop invariant that we apparently are assuming over here does imply the postcondition we're interested in, and that's precisely the third premise of the proof rule. That is precisely the first premise of the proof rule, and that is the second premise of the proof rule. So after reshuffling the order of the proof rules, this is a derived reasoning principle. We do syntactically get it for free out of the ones we already understood, and we'll of course just use the loop invariant proof rule instead of rederiving this proof again. Now, of course, there's still the challenge if you use the loop invariant proof rule from conclusion to premises, because remember that's the direction in which we use it, whereas that's the direction in which we justify validity of it. Then, well, we need to dream up this loop invariant J that we're using in a bunch of places here. But at least the way we've done the derivation of the proof rule informs us what we need to do in order to find such a loop invariant. Because basically, what we did here is we misplaced an alpha star box. And just like over here, we misplaced an alpha star box. And that means the kind of information that the loop invariant might have to transport along throughout the proof is knowledge about what was important in the history of the repetition of the loops so far, in order to make sure that we retain enough knowledge to be able to prove the inductive step, for example, that one more round is going to satisfy, but also in order to be able to prove that if the loop invariant is true at the end of this run, then the postcondition that we're originally interested in is true. Good. Let's use this new insights into how to do loop invariant proofs for repetitions in cyberphysical systems using this very proof rule that we just developed for some good. Well, admittedly, I'm first doing this on a very simple discrete loop, which isn't very cyberphysical, but just to get some of the insights across. When we're trying to prove this question, whether from some initial information, all runs of a discrete loop, never your mind, satisfy a postcondition, then we would apply the implies right proof rule, pushing the assumptions in the stack, and now apply the loop invariant proof rule to prove that in the beginning we know J. If the loop invariant is true, then after one round of the loop, is the loop invariant true again? And if the loop invariant is true at the end, then the postcondition we were interested in is true. Now, the question that we have when applying the loop invariant proof rule is, sure thing, but what specific formula are we using for the loop invariant J? One canonical choice is to say, why don't we choose the exact postcondition that we're interested in? Because if we use the postcondition x greater equals 0 for the job, it will be very easy to prove this third premise. Good. Here's our loop invariant. We're doing the proof, and sure, in the beginning we know x is greater equal 8, and that means we know that x is greater equal 0. And if x is greater equal 0, then by running this, that x is x plus y, we do know that x is greater or equal 0. Nah, wait, actually we don't know that, right? Because if we're adding x and y, then if y has very negative values, I guess x could actually be negative all of a sudden. So nope, that wasn't good enough. Or another way of seeing that syntactically is that this is the postcondition we're interested in, but that mentions the quantity x, which is changing right here in the middle of the loop, and how x changes reads the values of x and y, so we need to understand y in order to have a chance to understand x. Of course, we should have carried some information along about the history of the repetition that tells us that y isn't that negative. So I guess what we could do is copy-paste the initial condition, right? Because then it will be very easy to prove the first premise. Well, it will also prove the third premise, but it will be very hard for this loop invariant candidate to prove that it's still true after we're changing x to x plus y and y to x minus 2y, because, well, the whole point is changing it. So this is too strong, but that is too weak. It just changes immediately. I guess we need to retain some information about y in addition to the knowledge about x. So it would work if we would have a loop invariant that says both x and y are non-negative, because, well, then this addition will make sure that x is still non-negative. That's a good thing. We know this in the beginning. It would imply the postcondition. If we know that both x and y are non-negative, then after running this program, x is still non-negative. That's good. Do we know that y is still non-negative? No, we don't, right? Because we're taking x and subtracting 2 times y. That could become negative even if it wasn't. In other words, this loop invariant is also not sufficient for the proof. Apparently, the value of x has to remain really large enough to survive the subtraction of 2 times y. The next loop invariant that we can try is to prove that x is greater or equal to y and that y is still non-negative, which is true in the beginning if you look at it. Yeah, 8 at least is bigger than the 5 that is at most. If x is greater or equal to y and y is greater or equal to 0, then we certainly know that x itself must be greater or equal to 0. Now let's try and understand whether the induction step works out. So if we have that x is greater or equal to y and y is greater or equal to 0, then we're adding two numbers together. That one is greater or equal to 0. So after having added them, y is also changing. So we're subtracting 2 times y from x. But wait a second. X is at least y. So here, after having done that, we're at most subtracting y minus 2 times y. That's at least still 0, so that's good. So this side will work out. And because we've just added y to x, and y was non-negative, of course x has to remain bigger or equal to y because we just added them and x was non-negative. So yeah, that loop invariant works. You've now seen in one discrete case how you operationalize the intuition of loop invariant search as you think your way through what is the information I need to retain about the past evolutions of the system in order to make sure that the property we're actually interested in x greater or equal to 0 is really true in the end. We retain a bit more information than what we really needed just to establish the postcondition. But let's revisit this proof rule again, the loop invariant proof rule. It's just broken it because when we look at it, we've got some assumptions gamma and delta in the context. I copied them here, and I guess I forgot to copy them into the second branch and the third branch. I'm sorry, I shouldn't have done that. I probably should have had gammas and deltas here. For example, here, if we're proving that, then in the beginning we assume x is 0, and that of course implies the loop invariant x less or equal to 1. This loop invariant certainly implies the postcondition we're interested in. It was the same, and since we conveniently have left around the information from the context that x equals 0, then if we know that x equals 0 and the loop invariant holds true, after we increase it by 1, x is still less or equal to 1. So I guess that proof works. It shouldn't, though, because when we take a look at the sequent we just quote-unquote proved with this proof rule, it says that if we start x at 0, which by the way is less or equal to 1, then after we repeatedly add 1 to x, it will always remain below 1 at most. That's of course complete nonsense. All we need to do is run the loop 5 times and its value will be 5, which usually isn't a whole lot less than 1. In other words, it is actually not acceptable to have the initial assumption about gamma survive here. And likewise, you will understand that it's also not actually acceptable to keep the delta context here. Well, that should make us suspicious whether it is actually okay to make the context gamma delta from the sequence survive over here. Let's worry about that, right? Here's another question about the loop. If we choose x greater or equal to 0 as a loop invariant, then, well, certainly in the beginning, because x equals 0, the loop invariant x greater or equal to 0 will also be true. If x is greater or equal to 0, then if we add 1 is still greater or equal to 0, that will prove. And if at the end we have the x equals 0 assumption, together with the loop invariant that x is greater or equal to 0, we will of course be able to prove that x equals 0. So prove, quote unquote, with this proof rule, of that fact, but that's again very bad, because it simply isn't true that if we start at 0 and keep on adding 1 any number of times, that we will remain at 0. All you need to do is run the loop. How about 5 times again? So also over here it would be very bad if we would keep the context in any of those places. And in fact, that makes a whole lot of sense looking back, right? Because here what we have is assumptions about before we run the loop. We still have them when we're trying to establish the loop invariant J is initially true. That's the whole point. But in the middle of the loop induction, there's no way of assuming what we used to assume in the beginning. And also when we're done with the loop, there's no way of assuming what we used to assume in the beginning. In fact, from the derivation we've done for the loop invariant proof rule, because we were using Gödel's generalization proof rule and the monotonicity proof rule, it was completely obvious that we had to delete information about initial state because we're no longer logically in the initial state. Be very careful where your assumptions go, or your CPS might go also where it shouldn't. It's important to distinguish proof rules, as well as in the loop invariant proof rule, individual premises that are reasoning globally, such as here. This is reasoning globally. It shouldn't keep the context, whereas that one is reasoning locally. It can keep the context. Which one is local and which one is global? Well, admittedly, that's easier to see from the individual axioms we're using, which we've put together along with global proof rules to justify this proof rule. Let's take what we've learned and operationalize the invariant construction principles, but really now in CPSs. Well, maybe not quite in cyber-physical systems yet, but in our favorite mock-up cyber-physical system, the bouncing ball, you'll find at home as well. Let's put this to some good use by analyzing the repetition property of quantum, the bouncing ball. Remember, quantum, the acrophobic bouncing ball, was doing a bunch of bouncing, but it simply wasn't a whole lot of fun without a loop, because there's not that much bouncing without a loop. You can fall and then lie flat, but you can't click bounce, bounce, bounce anymore. So let's get back into the proof. The initial conditions are summarized by A. The supposed condition of being above ground and below initial height are summarized by B. And gravity is the abbreviation for the differential equations of gravity. First proof rule we apply is loop invariant proof rule, which requires us to find a loop invariant J, which of course will depend on the height and the velocity of the bouncing ball. That makes sense. And then prove that it's true in the beginning, prove that it implies the safety condition of the bouncing ball that we wanted, and prove that it is inductive. So if we're where the loop invariant is true, then the loop invariant is true after running just one round of the repetition. So look, repetition is here, is gone there, which in particular means that this is a significantly easier question because we can handle it with the dynamical systems axioms that we already saw. No more loops anymore. I actually should be telling you what this loop invariant is, specifically which formula, but let me try to see how far I can get away without telling you. So let's just continue the proof. There's not a whole lot I can tell you about this without revealing what J is, so let's make progress here. Of course, what we can do is work with the dynamical systems axiom for the non-deterministic choice. Let me just copy that same question up here again just to make sure I give myself a bit more space, and then use the dynamical systems axiom for the sequential composition to show that always after running first ODE, then discrete, whereas in the loop invariant, by proving that always after running the ODE, it is the case that always after running the control, the loop invariant is true again. Now, well, worrying about the ODE, well, it's going to give us a solution, it's going to be hard, but let's first split by the monotonicity principle that we saw the question into whether the loop invariant is true after the ODE. Remember, we can do that, and then prove that if the loop invariant is true, it's also true after running the control side. I could have kept them within one logical formula, but by proving with the monotonicity principle something helpful afterwards, and then working with it further on, I'm going to make the proof a bit easier for us. Now here, this side, we will continue to work further, because the ODE I would like to very much postpone. Here, what we do is work with the non-deterministic choice. All behavior for non-deterministic choice makes the loop invariant true if all the left behavior makes it true and all the right behavior makes it true. We have a conjunction to worry about. We can split by the and right proof rule and all the left behavior and all the right behavior. Here we have a sequential composition to worry about, which of course means always after the test, we need to show that always after the assignment, the loop invariant is true. Now we've got the test to worry about, which after converts into an implication, which right away with the implies right proof rule moves the assumption x equals 0 on our list of assumptions, and leaves us with the assignment to be worried about, which we can substitute in. This leaves us with the question whether if the loop invariant is true and we're on the ground, then the loop invariant is true again after we inverted the velocity to minus damping coefficient times velocity. Can't make any more progress without thinking about what J really ought to be. Over here, we've got a test. So again, by the test proof rule and the implies right proof rule, which didn't fit on the slide, we can assume x not equals 0. We assume that the test passes, and then prove that the loop invariant is true after without any change to anything. Well, let's look at the open premises of this proof. These ones right here, where of course it now really becomes important, all of them, what is the loop invariant really? One way of understanding what we just did is we're trying to discover what are the conditions that a loop invariant must meet. Let's write them all down, all the right formulas here. And let's resolve the abbreviations. So let's plug in the concrete condition for the initial condition for A, and the concrete safety condition being above ground for B, and the concrete differential equation for gravity. There we go. Still need to figure out what the loop invariant J is. What could it be? Could be just the post condition. That's always the most canonical candidate, because if we choose the post condition for the loop invariant, it will be very easy to prove that the post condition is afterwards true, because we just chose exactly that. So that'll be a piece of cake. But what about the ODE? If all we know is that we're still above ground, then running this differential equation doesn't make sure we're always above ground and below the initial height, because even if we are below the initial height in the beginning, if our velocity is pointing upwards, we very much will fly higher. So that will not work out. It's too weak. It fails if the velocity is bigger than 0, for example, a lot bigger than 0. Well, I guess that makes some sense, because if we would like to show something about the position, the differential equation makes the position depend on velocity, so unless we also show something about velocity, we will never be able to prove this proof. And that means our loop invariant needs to carry forward knowledge about both of those. We could maybe just prove that we're above ground. That will make this differential equations property work out quite easily, because, hey, the evolution domain constraint even assumes that we're above ground. So that will be a piece of cake. But now, where's the trouble? The trouble is that we will no longer be able to prove the post condition from that. The left conjunct is a piece of cake. If we're above ground, I guess we're above ground. But we're not really below initial height if all we know from the loop invariant is that we're above ground. We didn't carry enough information around to make a post condition happy. So we could use something like we're on the ground with velocity 0. That will most definitely make the differential equation prove, because if we're on the ground with velocity 0, we can't do a whole lot of falling. If we're on the ground with velocity 0, we'll definitely be within the initial height constraints as well, because, well, on the ground or below initial height. Where's the trouble now? Trouble is that we will not be able to prove it in the beginning, because in the beginning all we know is that our velocity is 0, check. We're at initial height, which is above 0, but it doesn't have to be exactly equal 0. And in fact, the bouncing ball would be totally bored if we would prove just that it bounces safely if it doesn't actually move. We still need to link it somehow. Well, maybe we could try that we're on the ground, or we're at the initial height with velocity 0. That would prove all kinds of beautiful things, but it isn't actually inductive because, for example, it doesn't rule out that we're ever so slightly below the initial height, say 90% of the initial height, or even 99% of the initial height, with a velocity that's a million pointing upwards, and of course we will never make sure this property is true afterwards. Yeah, that's just a discontinuous space even. It's not connected. We know something about 0, and we know something about initial height h, and we don't know anything in between. That can't be inductive. What we can do is remind ourselves about what we did when we were just proving intermediate conditions for bouncing balls, and recall that what we really did in the proof is to show that 2 times gravity times position is the same as 2 times gravity times initial height minus v squared, and by the way, our position is above ground. And if you choose that, which you also see motivated carefully in the textbook, then each of those conditions will actually be able to prove. And it indirectly, implicitly gives us the link between velocity and position that we needed for the proof to have a chance to work out. And the defining thing that enables us to inform such a decision is the link in the differential equation, because that's the ultimately thing we need to make happen here. The discrete parts are proved. So that leaves us with these things of arithmetic, and yes, they're all proof. Let's look at that one, for example. Here, if we assume this loop invariant, then we need to show that it's still true with minus c times v square instantiated. Well, actually, that we only really know if the damping coefficient was 1, because otherwise this would have damaged the equation a little bit. Well, all right. Yeah, how about we assume that the damping coefficient is exactly 1 at the moment? That at least makes our lives easier. Oh, I guess we need to be more careful here. This one now works out under that assumption. What about the others? Here, well, that's good. This conjunct implies that because it's the same. This conjunct implies that because it's the same. Actually, looking back more carefully, we would have always been able to prove this fourth branch just from the syntactic criteria on it. So that would have been always easy. Let's worry about the last one, whether it implies the pose condition. Yeah, it does. This part is immediately implied. We're above ground if we're above ground. We also must be below initial height because the two are linked and we're subtracting a square, so a non-negative quantity from it. So x can't be any bigger than that if they're supposed to be equal. Whew, good, that worked. But actually it only worked because gravity is a positive constant. Because, for example, if gravity were 0, the argument wouldn't really work. I guess we need to keep this information around somewhere in our assumptions. That leaves us with the initial condition. That's now actually easy. And this time, I promise, we don't need additional assumptions, because if the velocity is 0 and we're exactly at initial height, then this equation is really easy and we're apparently above ground by initial condition assumption. So we're left with the hardest one, the question whether during the differential equation the invariant is preserved. And if you think back, we actually almost already proved that. So, but before we do, let's reintroduce the abbreviation J that we used for loop invariant, just to save some space. Move this question to a new slide. Do a careful proof with it, where now we use the dynamic axiom for solving differential equation, which gives us the question whether for all times the solution of the position at the velocity makes the post condition work out. And we have already argued last time why it is okay and a bit easier for our purposes to just do this under the assumption that the evolution domain constraint is merely true at the moment, as opposed to even if that would be true, if the evolution domain constraint has been true at every intermediate time. It just makes it fit on the slide a bit easier. So we have the sequential composition that we need to split into two separate parts. Then we plug in the velocity by the assignment axiom to have minus g times t for the velocity instead, and we plug in the position here and there in order to show that if we're above ground, then the loop invariant is true for that new position and the new velocity. We have to prove this for all times now. So for example, we can use the for all right proof rule. Then we can use the implication proof rule to move all the assumptions on the left-hand side. So we use it repeatedly, once here and then once there. And then this is the remaining arithmetic question. Beautiful. Let's expand the abbreviations of what the loop invariant really was. That is this question now. That we're able to prove because the conjunction we prove separately. So we need to prove the left-hand side and the right-hand side conjunct. The left-hand side conjunct, we've got 2gx equals 2gh minus v squared. What do we have over here? 2gh, well that's good. Minus 2 and the half cancel, and the g give me g squared, and the t squared. So that needs to be equal to whatever we said on the right-hand side. So proving the left-hand side conjunct, that will be easy. 2gh, well that's 2gh, and 2g squared with the half, that makes this 2 and the half drop and gives us a g squared times t squared. Well, that's exactly that, of course. So yes, this part of the arithmetic works out even without the assumption. We could have weakened it away. Remember, that makes the arithmetic a bit easier if we weaken away irrelevant assumptions, but never you mind for that for now. And the right-hand side, oh, yeah, that proves this very easily by identity. Brilliant. We have a proof of the bouncing ball. With repetition. But with cheating. Is quantum really done with a safety proof? Not quite, because the solutions we've sneaked into this when using the solution proof rule are pretty fine solutions if we start at the initial height and if we start at the initial velocity 0, which of course we do when the bouncing ball starts flying around for the very first time in his life, but we're in the middle of an induction step, remember? What we know at the moment is that J is true, and the loop invariant very much leaves open the opportunity that positions and velocities could be different, because that's its entire point. It's trying to capture everything we ever knew while this was going on. And that means these assumptions are not available here, and we have to redo the proof with new solutions. In other words, the more important lesson for us going forward is that we really never should be accepting solutions of differential equations without right away first going for a proof of this. Of course, that's precisely what a theorem provers do. They don't just write down solutions of differential equations, but right away prove them to be true as well. Okay, in addition to accidentally having solved differential equations from the initial state, quantum was clumsy also because he misplaced the constants. Remember, in the middle of the arithmetic proving, we suddenly found out that quantum desperately needed to know that the damping coefficient is exactly 1, and the gravity constant is positive. And of course, you get into trouble if you just randomly dream up extra assumptions in the middle of the proof. How do we make sure those assumptions are actually available when we need them in the proof? Recall, we can't just keep the initial assumptions from the context around innocently, because some of those, such as initially velocity 0, stop being true after some amount of evolution of the bouncing ball. That's the whole point. Bouncing balls don't want to just always have velocity 0, they want to move. So, how can we help poor quantum get its proof worked out correctly? With these initial parameter assumptions, well, intuitively, they ought to be always remaining true anyhow. That's what's called an invariant. So let's put it into the middle of the invariant by augmenting our loop invariant with the one we already had from before and the assumptions on the parameters. Now that requires us to do a new proof. Same question, bouncing ball is safe. That leads, with the loop invariant proof rule, to the question whether the conjunction that is the loop invariant of the old one and the new parameter assumption is true in the beginning, and of course it is. That's the entire point. The damping coefficient is 1 and the gravity is positive was one of our assumptions within A. Now it also leaves us with the question whether the new conjunction as a loop invariant implies the postcondition, and whether the new conjunction as a loop invariant is actually inductive. So if it's true before one round of the bouncing phase, then it's true right after as well. Can't just wave our hands on that. We have to be more careful in conducting a proper proof. Let's do so. We could repeat the entire previous proof and be asked everywhere whether the conjunction remained invariant. That would work, but it would also be very annoying. Instead, we can be clever about how we conduct the proof by splitting a universal box property of a conjunctive postcondition in two separate ones using this proof principle. After all runs of alpha is P and Q true, if and only if, after all runs of alpha is P true, and after all runs of alpha is Q true. If we use that here, we split the question whether the old loop invariant is always the case, and separately whether the new loop invariant with the parameter assumptions is always the case after one round of ODE and control. Look at this distributivity law for boxes in conjunction. It should remind you a little bit of what the axiom of choice does, but recall that the axiom of non-deterministic choice split the hybrid program properties and kept the same postcondition in all the places. This here thing instead splits conjunctions and postconditions of box modalities into separate sub-questions. But it still decomposes. But this time we decompose the postcondition. That's still oftentimes a useful thing to do. Not always, because if P and Q are sort of preserved for the exact same reason, it's easier to worry about them simultaneously. But here the point is they're preserved sort of for different reasons. So on the left, we then split the proof with the and right proof rule to worrying separately about whether J is inductive, so it's still true after alpha runs, and whether P is still true after alpha runs. Then this proof is really the exact same proof as we just did a moment ago, except that we now have the additional assumption, which was the whole point, of the parameters available. So we really know that C is 1 and G is positive, so that proof will actually work. On the right, well, we could split up the hybrid program alpha with its ODE and controls and so on again in order to prove that the parameter constants are still parameter constants, but oh boy, is this boring. Intuitively, it should be kind of sort of clear that the parameters or whatever values they had before still have them right after, because alpha doesn't even touch the damping coefficient or the gravity constant. Even the most amazing bouncing ball wouldn't change the laws of gravity around. And here's the proof rule for the job. It's actually an axiom, the vacuous axiom, which is not because it's a bogus axiom, it's because it is meant for vacuous change, so things that don't actually change. If a formula P, such as the one down here, is true, then it's also always true after running a hybrid program alpha. Whoa, hold on a second. Not, of course, that cannot possibly be true for all postconditions P, but it is true for postconditions that don't change for obvious syntactic reasons during the hybrid program alpha, which means that the free variables of the postcondition intersect that the bound variables of the program is the empty set. That means the variables that the postcondition is reading, the one that it's depending on, such as here, damping coefficient and gravity, are not changed in the hybrid program alpha. And of course, the hybrid program changes all kinds of things, positions, velocities, but it leaves gravity and damping coefficient alone. It merely reads them, it doesn't change them. And using this vacuous axiom, we can see that because P is one of our assumptions, it is obvious by the vacuous axiom that after running alpha, which doesn't change any of its parameters anyhow, is P true again. So this proof is a one-step proof, much easier. In fact, for these reasons, because constants are so obviously preserved, we often actually elide them from the loop invariant and simply use this magic in order to make sure our assumptions about constants survive our arguments along the way. Let's wrap up. We have now an actually verified cyberphysical system, okay, hybrid system, quantum, the provably safe bouncing ball. Here's the differential limiting logic formula that now has an absolutely rigorous proof, including the non-deterministic repetition, the differential equations, and the discrete control, and the property that it's always above ground and below initial height. Unfortunately, only under one additional assumption that is not technically necessary, but we needed it in the middle of the proof just to make a proof a bit easier. The one that says that the damping coefficient is exactly 1. Good exercise. Don't worry about how you get rid of this assumption. We can also remember a few chapters ago that we were starting with tracking requirements and ensures contracts as preconditions and postconditions in our program. We can now capture all we need as assumptions, as preconditions also on the parameters, and postconditions that we're ensuring, and also transport the most important insight in the proof, the one that says the non-deterministic repetition has as loop invariant this particular logical formula that we've used. Notice we leave out the constants because they're kind of obvious for humans. Invariants play a crucial role in CPS design, which is why you should be capturing them if you can. Always write them down with add invariant contracts in your hybrid programs. First of all, this helps the human designer when he's understanding your program. Also, when another CPS programmer is changing your program, they will know what you need to be preserving in order to make those changes be correct. Or if you do that 2 weeks from now. And these invariant contracts also help simplify the proof a whole lot. Wrapping up, what have we seen today? The fact that the lion's share of understanding in CPSs comes from understanding what does change. That will be variance and progress measures that we will ultimately see, and fundamentally what does not change, the invariants. And it turns out that invariants are a fundamental force of computer science and many other areas of science as well. But variants are another fundamental force of computer science. Whenever we worry about what a CPS does, the dual pair of knowledge of what does not change and what does change and in which way essentially tells us almost anything we ever need to know about these systems. Keep them in mind very carefully, which also means that the search for these invariants and the understanding is one of the most subtle parts in the entire game. What we have done is develop the induction axiom that says always when repeating a non-deterministic repetition of alpha for any number of times, we're always safe, if and only if, well, we're safe right now, and always when repeating the non-deterministic repetition, if we're still safe, we're safe again for one more round of alpha. And the two sides are equivalent, so we can equivalently replace the left by the right. The way I remember the admittedly somewhat more useful loop invariant proof rules out of that is to simply say what they do is replace this side by that side and get rid of the box modality that we have here in order to make sure that we're not reducing properties of loops to other easier properties of loops using Gödel's generalization proof rule that says if we have a proof of P, we also know that P is always true after running alpha. And relatedly, the monotonicity principle. If P implies Q, and we have a proof of that, then if P is true always after running alpha, then Q is also true always after running alpha, because whenever P is true, Q is true anyhow, and since P is always assumed to be true after running alpha here, we can easily see that Q is always true after running alpha as well. Now, this means Q is easier to satisfy than P because P implies Q. The loop invariant proof rule simply derives from these, but it's useful to remember in any case because we need it so often. From some initial assumptions, all the repetitions of alpha satisfy the safety property P, or some other alternatives. For that, we find a loop invariant J that we prove is true initially, or the other alternatives. Then we prove that this loop invariant is preserved when running one round of the loop as opposed to many rounds of the loop. And we prove that the loop invariant retains enough information to imply the post-condition we were originally interested in. Another slight twist on the monotonicity principle is what we used here, just a cut rearrangement of it. It says that proving the P property is always true after alpha can be reduced to proving the Q property is always true after alpha in any context if we separately convince ourselves by a proof that Q also still implies P. So in other words, we can strengthen postconditions, which is precisely what this expresses in different ways. We've also seen that it can be useful to split conjunctions and postconditions of box modalities because all runs of alpha satisfy P and Q, if and only if all runs of alpha satisfy P, and independently all runs of alpha satisfy Q. And we've seen the vacuous axiom, the one that says, well, but if P is true before running alpha, it is also always true after running alpha. For obvious reasons, if only we make sure that the variables that are free in P, the ones that it is reading, have nothing in common with the variables that are bound in alpha, so the one that alpha is writing to, the ones in assignment and differential equations. And that now finishes up everything we ever need to know as proof techniques for elementary cyber-physical systems. Now we're able to handle all elementary cyber-physical systems with non-deterministic repetitions that we just talked about extensively today, non-deterministic choices, assignments, differential equations, and tests, out of which you can define all other operations in elementary cyber-physical systems as well. In fact, you can also define properties with advanced cyber-physical systems where the difference is that the differential equations are more complicated as well because they don't have solvable ODEs. But that we'll get to a little bit later in the textbook.